so now we can define using Friedmann's equation, the first Friedmann equation. We can define this is the energy density of the universe today in terms of the Hubble constant. Remember that I assumed the universe was spatially flat, and this has a consequence that the density today has to be in a special value, and this is called the critical density. So this is just the the first Friedmann equation written in terms of the Hubble constant today. So this is the critical density today, and in fact we can what we do is that we construct another variable called omega, the capital omega, for each species of that contributes to the energy density budget of the universe. And that's in relation to the critical density. So just knowing that the universe is flat means that we are at the critical density. So we know what the critical density of the universe is today. So if you measure the Hubble, you know exactly what is the critical density today. And I don't know if I give you as an exercise, nice exercise. If you just plug in the value of the Hubble constant, it's around 70 kilometers per second per megaparsec, and you do the appropriate dimension, use the appropriate dimensions, you will compute what is the average. So this is the critical density, the average critical density of the universe today. And just to give you a spoiler, you know what's the critical density of the universe today? It's equivalent to more or less 5 protons per cubic meter. That's the critical density of the universe. So you can imagine that, so this would be the average density of the universe today. So we are very, very huge fluctuations around about this critical density, okay? So this is a nice exercise. Try to do it. And you see what the critical density is in units of GeV per cubic meter. And that's 1 GeV is more or less the mass of the proton. So you find that's around 5 something GeV per cubic meter, the critical density today. Anyway, so we measure different contributions to the energy density budget of the universe in terms of this variable capital omega I, which is the ratio of the energy density in that particular component, say baryons or photons or neutrinos, dark matter, dark energy, whatever component you have with respect to the critical density. And of course, if you sum them up, you should get 1, because the sum of all the densities should be the critical density today. So that's what I mean. In a spatial flat universe, if you add all the components, this omega I of all the components, you get 1. And you can rewrite the first Friedmann equation in a very convenient way as a function of this omega i's. When I put this upper index 0, it means today. So be careful when I say that. This is today, and age 0 is the Hubble constant today, and age of t of time, of course. Then you can solve Friedmann's equation, and you can, so I have some exercises here. You can do it at your own leisure. And also, you can, given the initial conditions of the universe, say the values of this omega lambda, which is around 0.7, omega matter, which is around 0.3, omega radiation, which is around 10 to the minus 5, you can just plot the evolution of these different components very easily. So I think I have a Python Colab notebook that I can make available for you to plot these things. It's really easy. Okay? So again, this is just to show you the different, we usually work with these variables capital omega, which is the ratio of the energy density in a certain component to the total energy. It can be at most 1. So this plot here is log of A. So this is today. Today, of course, you have 0.7 of omega lambda, which is the green one. You have around 0.3 of the matter, and radiation is very, very small. And then when you go back in the history of the universe, it's dominated by radiation. And here is the equilibrium point, or the equipartition point between dark matter and dark energy. And this is dark matter and radiation, matter and radiation. So that's very easy to do, okay? So I make this. Do you know, I'm not a very good programmer, but you know Python Colab, this, So this is anyone can do it, right? You don't need to have Python in your notebook. Okay. So I think this is the end of the first lecture. So let's see if I can do this correctly. Where's the double tap? Ah, here. Okay. So let's close this and start the second lecture. Should work. Okay, so let's start the second lecture. The second lecture, this lecture, I'm going to talk about, again, as a continuation of this, describing the average universe, and just to set the notation, etc., for all the lectures. So I'm going to talk about how to measure distances in the universe. There are two major parts, distances in universe and thermal history. So this is the plan for this lecture. Two kind of disconnected parts, distances, horizons, etc., and then how the evolution of the universe changed the temperature and the thermal history of the universe. Okay, and again, feel free to ask questions anytime. All right. So the first part of the lecture will be divided into this. I'll talk about the difference between physical and comoving distances. I will introduce the luminosity distance, talk about distance ladder, the accelerated expansion, then a little bit of the angular dynamics, and then the Hubble radius. This is the plan for this first half of the second lecture. So about physical and comoving distances. I think I already mentioned this a little bit in the first lecture. A physical distance as a function of moving distance. Moving distance is the distance of objects in the average universe, discounting the expansion rate. So if you do expansion rate, they just don't move. They are co-moving, let's say. That's the word that people use. And the relation between a physical distance and a comoving distance is this scale factor, as you would expect. So I try to keep this notation that the physical distance I call r, which depends on time, and the comoving distance is x, which does not depend on time. Okay. Now, so there's a jargon here that we say that galaxies follow the Hubble flow. So what is the Hubble flow? Is this expansion of the universe? Just how the expansion rate, how the scale factor changes with time. So this is the Hubble flow. And the Hubble flow has a speed related to it. And this velocity is we can compute by calculating the time derivative of the physical distance, which I call a velocity v. And of course, I can rewrite this in terms of the comoving distance, x. So the time derivative is just a time derivative of the scale factor. And then I multiply and divide by the scale factor again, and I get r. So this is, this is a very trivial way of recovering what is called the Hubble Law, which is the relation between a velocity and the distance. So the velocity is proportional to the distance. So this is, again, an approximation, and I have to make this clear. In reality, in addition to this Hubble flow that the galaxies are following, there will be some peculiar velocities, because the universe is not homogeneous. So there will be some peculiar velocities due to the fact that there's more matter here than there, and the galaxies will be more attracted towards where there's more matter. So this, we take that into account later, but not this time, okay? I want to answer now is how to measure distances and velocities in the universe in practice. So to measure velocities, we don't measure velocities directly. We measure what's called the redshift, and that's given by taking spectral lines and see how they are displaced with respect to the spectral lines of elements in the laboratory. And this is a proxy for velocities, but we actually talk a lot of redshifts and not velocities. This is why you want to measure the redshift. You have to take the spectra of galaxies and then analyze the spectral lines and measure the redshifts. So that's what you measure a redshift. This is one way of doing it, and then I'm going to talk about this a little bit later, but there's another way of doing it, because taking spectra is difficult of galaxies. So there's another way, which is taking photographs in different filters, and that's called photometric techniques. And the series of galaxies these days, there are two major types. One that uses spectroscopy, taking spectra of galaxies, and the other that uses taking pictures of galaxies in different filters. So those are called spectroscopic surveys and photometric surveys. So I talk a bit about this later. So this is how you measure redshifts. Now, how do you measure distances? So to measure redshifts is very easy, okay? Easy. Taking spectra. Distances is much more difficult. I don't have a ruler that goes to the Andromeda, right? How do I measure a distance in the universe? So, so this is what I'm going to talk a little bit here. So first of all, we have to define a few distances. One distance that is basic for all the other is called the comoving distance between us and an object. So us, we are at a redshift 0, and an object that is at some redshift z, arbitrary. And in these lectures, I'm going to take the speed of light equals 1. So you have a light ray that goes from here to another object at the redshift z, or the opposite. And the distance, of course, of a light ray, the invariant distance is 0, because it's a light ray, it goes on a light curve, a light path. So, so using the Friedman-Lemaitre-Robson-Walker metric, you get that dt square is just a square times what is called the comoving distance, d chi squared. So you can integrate this, and you get that this comoving distance, again, between us and an object at the redshift z, is this integral of 0 to z of 1 over the Hubble parameter z. Okay, I can derive this. It's not difficult from this equation. You just have to change variables from the t to the a, and from the t to the z, and you get this this integral. It's not difficult. I assure you, it's not difficult. And again, we can derive this later if you want. So this is what's called the comoving distance, which actually is not directly measurable, but it's a useful quantity in cosmology. And this is interesting because this distance depends on the cosmology through the Hubble parameter. Remember, the Hubble parameter depends on the Hubble parameter depends on the cosmology, right? It depends on the amount of dark matter, dark energy, etc. Through the first Friedman equation. So this is, again, this is the comoving distance, which is going to be used to define other distances. Another useful quantity is what's called the horizon at a given redshift. So it's very related to the comoving distance we just mentioned. It's the comoving size of the causal region since the Big Bang. And the Big Bang happened when redshift was infinite until a given redshift z, right? So this is this is the definition. It's very similar to this one. I don't know why I kept c here, but it's the same thing. But now it's the integral between redshift z and infinite. And I know why I kept c, because later to define what is called the sound horizon at the coupling, at the coupling with radiation, and then we substitute the speed by the speed of sound of the fluid. So this is called the horizon at a given redshift, okay? Again, very similar to this equation, just the limits are different because the interpretation is different. Yes? Ah, very good. So is the causal region is when a light ray can reach you. So if you have if there is a region where the light ray at a certain redshift cannot reach you, you're not in causal contact. So those are light rays that are reaching you from a redshift, this Big Bang up to a redshift z. Okay, so this defines a region where information can be exchanged, because you can exchange light rays, basically. So you can exchange information. So thank you. This is what I mean by causal region. Thank you. Yes. 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 Everything in these two lectures is average.
Why you are using Z for the Hubble
Sorry, I'm using the redshift as a measure of time instead of A. Yes. So the original integral was in time. Thank you for the question. So the original relation was with time. So chi of z would be an integral of dt over a of t. But then if you do all these manipulations, you get this z over h of z. It's just changing of variables from time to z, to redshift, because sometimes it's more convenient to work with redshift. Thank you. Oh, 0. It's because it's a light ray. So light ray follows no trajectory, so meaning ds equals 0. Good, thank you. Any other questions? Good, it's good that you're asking questions. So you continue. Ask questions, okay? Okay, so as I said, in the universe it's easy to measure redshifts using spectroscopy, but measuring distances is much more difficult. So basically, there are two ways of measuring distances in the universe that I know of, at least. And one is using what is called the luminosity of an object. And then the idea is very simple. You know this intuitively. So if you know a car that has headlights on during a night, and the headlights is very bright, you know the car is next to you. If the headlights is very faint, you know the car is away from you. So, but for doing that, you have to have an intuition of what is the intrinsic brightness of these headlights, right? So the idea is in this kind of luminosity distance is to have a standard candle. So what is a standard candle? It's like, suppose you have a 100 watts light bulb, right? So you know the intrinsic luminosity of a 100 watts light bulb. If you measure this light bulb, the luminosity of the light bulb, if it's 100 meters from you, or if it's 500 meters from you, the luminosity that you will get in your detector, in your eye, is going to be different. So by comparing the luminosities with the intrinsic luminosity, you know what the distance is. So this is one way of measuring, physically measuring the distance of an object. And that's called luminosity distance. And the other way to measure a distance is what people do when they're measuring the size of a building with this, what's called theodolites, theodolitos. I don't know how to say that. It's teodolito in Spanish. So teodolitos, right? You have something, you know what the size is and the angle, and you can calculate the distance, knowing the angle and the size. So you have to know an absolute size of in the universe, right? An absolute size and the angle. If you know the absolute size and the angle, you have your teodolito, and you can calculate the distance, okay? And these are called angular diameter distance. So it was shown that some type of supernova explosions called supernova type 1a, they can be standardized. So people, by looking at what's called the light curve of this special type of supernova, you can measure, you can estimate the absolute luminosity. That's very interesting. How people did that, it's a long story, fascinating story, and yeah, I can tell more about this. And then also, more recently, people are using standard rulers in the sky, and one is the baryon acoustic oscillation, the other one is someone already mentioned the first peak of the cosmic microwave background angular power spectrum, which I didn't talk about, but I will. Or Julian also will. So there are these two types of distances that one can actually measure in the universe. And this gives you information about the model of the universe, because they depend on the model. Okay? And this is an illustration, just an illustration, of these two different types of distances. This is supposed to be an illustration of the luminosity distance of a supernova exploding in a galaxy, and this is supposed to be a standard ruler, which is the distances between galaxies in the universe. Okay? So now I show you the definitions of these distances in terms of the comoving distance, for instance. Yes? Yes. So that's a good question. So let me repeat the question. Verdad is asking about the parallax. So what is a parallax, first of all, for maybe for people that don't know? Parallax is the reason why we have two eyes. If you close one eye, you lose the F, right? So you need two eyes in order to see the difference between the distances. Some background, yes.
So when we say it is hard to measure the redshift of light sources, because if we had a binary black hole, for example,
Yes.
instead of measuring flux,
Yes.
we're measuring the waveform amplitude and phase.
Yes.
And then it would be easier to measure luminosity. There's only one object of such a compact coalescence with a known redshift.
Well, yes.
Roles are reversed, I guess.
So there is a whole, yeah, so there's a, let me answer Merdad's, and then we go here. So Merdad is asking about parallax. And parallax, yes, you can use, so parallax you need to observe an object from at least two different points in order to have the angle, right? And parallax is actually used, so what's the limitation of parallax is the angle. So what do we use to measure parallax is actually the orbit of the Earth around the Sun. So there, the arm length is the distance of Earth to Sun. And from that you have to measure how a star deviates from the background stars. So this is the parallax angle. By the way, do you know what a parsec is? It's a distance, right? But you know what the definition of a parsec is? It's the distance where the parallax angle is one arc. That's where parsec comes from. So there's a limitation of the angle that you can measure. That's the main limitation. So with observatories on Earth, this was a very limitation because you cannot really measure very small angles. There's fluctuations in the atmosphere, etc. Now with Gaia, there's a satellite called Gaia, which is measuring billions of stars in our galaxy and with very accurate angles. So the Gaia has has incredible, I forgot the numbers, but has an incredible sensitivity to measuring parallax. And this has improved our knowledge. So maybe, sorry, before getting to, I just want to answer a little bit better. There is something called I think I mentioned this, the distance ladder. So what is the distance ladder? Is that we measure a distance of objects with some precision using some technique, for instance, parallax. And then with that, we can calibrate some objects with some luminosity, for instance. And then if you see this object at a larger distance, we use this calibration to estimate the distance of further objects. This is done with supernovas, for instance, right? So I have a plot of this, of supernovas, of Rees, the distance ladder. So I'm not sure if I answered your question about parallax. So parallax has limitation of the angle because the arm length of the parallax in our observatories on Earth is the distance between the Earth and the Sun. And the Gaia satellite is doing much better sensitivity on this. But again, this is not very good to measure very long distances. Now, your question is about gravitational waves and how to measure luminosity distance from gravitational waves.
So there was a statement that is to measure the distances of objects like redshift. That's for light sources, I guess, because if you had
Oh, absolutely. So yes, absolutely. You're right. So this is for light sources. Why? Because redshift, by definition, is the shift of spectral lines. As far as I know, gravitational waves, they have, of course, they have a waveform, but I'm not sure how easy it is to compare. We don't have a waveform at here, right? So, so there are other ways. I think for gravitational waves, you need to rely on the redshift of the host galaxy or whatever. So it's difficult, and people talk about bright sirens and dark sirens, and I'm sure that Riccardo Sturani will mention a lot dark sirens and bright sirens to have an influence on cosmology. So I think right now you need a bright siren to have a cosmological inference using black hole mergers, because you need to know the host galaxy. So you need to know where you have to have a magnetic counterpart. So thank you both for the questions. Any other questions? So we're going to talk about first luminosity distance. So what is the luminosity distance? In a very practical way, you receive in your detector some flux of photons. So the detector is at scale factor 1 or redshift 0. That's in your laboratory. And this is the known luminosity of the source, which is energy per time, and this is divided by the area. It's just the fact that the luminosity, the flux of energy decreases with the area. The flux of energy per area decreases as you are farther away from the object. So in Friedmann-Lemaitre, Robson-Walker, there are two sources of dilution of the flux factor. First, the redshift of the photons, so the photons lose energy due to redshift. And second, the frequency of arrival decreases by a factor of redshift 2. So there are two factors that you have to take into account when computing, D sub L is the luminosity distance. So in order to compute this luminosity distance, you have to take account of these two factors. And in fact, you can show that the luminosity distance is related to, this chi of z is the comoving distance. And this is the relation between the luminosity distance and the comoving distance. So this is not difficult to show. I can also show if you are interested. And then something nice to do is that you can Taylor expand the Hubble factor to the Hubble function to first order in redshift and plug it in here, because there's a definition of Hubble. The Hubble enters in the integral of chi of z. And what you get is the relation between the luminosity distance, that's what you measure, with redshift. And that's what's called the Hubble Lemaitre law. There are corrections of other z squared. Be careful. Okay, so this is for small redshifts. Okay, and so this is the Hubble law. Actually, yeah, I want to show you that now the correct way of calling Hubble law is Hubble Lemaitre law, and this was by a meeting of the International Astronomical Union in 2018. And I think it's very well deserved, because Lemaitre was actually the first one to understand the expansion of the universe. It was not Hubble. Again, if you read Hubble's 1929 paper, there's no word of expansion. The expansion word is not written in that paper. And I can tell you why, but not now. So it's the history is amazing. So this guy is Georges Lemaitre, who was a priest. He was a Catholic priest in Belgium, but he was a physicist. He actually did his PhD in Cambridge and studied at MIT, and he was really incredible person. And his work of 1927, it's all there. Now he didn't know about Friedmann's equation. He rewrote Friedmann's equation. He actually had a physical interpretation of the expansion of the universe. He actually used data that was available then to derive the Hubble constant. So he was the first one to derive what we now call the Hubble constant. And he actually got the result that was very similar to Hubble's result, because there's no error bars, and you can draw any line here. Something's happening. What should I do now? I'm getting the hang of this. Anyway, so this is the plot, a more recent plot. And this is, again, velocity per distance. And here in this little red corner is Hubble's data. So we see that now, yes. Oh, I screwed up. Okay. Okay, thank you. That's fine. Okay, so this is a Hubble Lemaitre law, and much more linear fashion. Of course, this doesn't continue forever, as we will see. This is good. You have error bars. You see that you have error bars in distance, but no error bars in redshifts or velocities because the errors are much smaller in redshifts than distances. And I like to show this plot just for historical reasons. This is a plot that Robert Kirshner put in this paper of 2003, showing different measurements of the Hubble constant as a function of time. So you see that when first measurements gave the Hubble constant around 500, 600 kilometers per second per megaparsec. So it was off by a factor 10, the first measurements. And you know why? It's called systematic errors. I can explain later, but they had two, there are two different families of Cepheid stars, etc. Anyways, so this thing converged after 1960s, and then, but again, you know, it was between 50 and 100. So I remember this clearly when I was young, that people were discussing the Hubble constant was between 50 and 100 kilometers per second per megaparsec. And then there was a revolution of precision after Planck. And that's the plot I think I showed before. And this is the measurement. I think this is the distance ladder I was mentioning before. Yes. 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 So Hubble was here. Yes. So I think the question was what was this little corner here? And this little corner here is the data from Hubble was in this little corner. Just to see how, you know, how much better we're doing since 1929. Okay? Right? And of course, this plot cannot continue forever. And then remember, this is for small redshifts. So there will be modifications which are related to the expansion acceleration of the universe. Okay, so this is just a historical plot. And this is something that you should notice. It's very important, actually, is measurement of the Hubble constant from this ladder process. No? So we start with this stars called Cepheids, which you can measure the relation between period and luminosity using parallax, actually. So you use parallax to calibrate the relation between period and luminosity of this certain type of stars called Cepheids. And this is a story also. I mean, the relation between luminosity and period of these variable stars was established in the beginning of last century by an astronomer called Henrietta Wivet in the US. And the story of this is also incredible. Anyways, so there's this variable stars called Cepheids that has a relation between period and intrinsic luminosity. So if you measure the period of this, so stars that varies with days, you can have an indication of the luminosity. Then you use these Cepheids in other galaxies to study other galaxies, and there can be supernovae in other galaxies, so you also measure supernovas and you also calibrate. So there is a whole ladder of calibration. So geometry, this is geometry I think is meant parallax to Cepheids and Cepheids to supernovas. And this is what I think is amazing. So remember this plot here. You see there was a spread between 50 and 100 kilometers per second per megaparsec. And after this amazing work of Rees and his collaborators, now the uncertainty in the Hubble parameter measured by supernova, by local probes, not from CMB, I think we heard more about that, you get a precision of almost 1%, a little bit above 1%, 1.2, 1.3% in the Hubble constant, right? So again, this was between 50 and 100 a couple of decades ago. So now I'm starting to remember time by decades. That means that I'm getting really old. So a couple of decades ago was between 50 and 100. And now we have this amazing precision in the measurements of the Hubble constant using nearby objects, not too far away. And this is to be compared with the CMB indirect measurements And this is bringing some tension to the field, which is very nice. So yeah, so you can also compute the luminosity distance at higher redshifts. You can expand to second order this relation, and you actually get something like this. H0 times the luminosity distance is proportional to z. So that's the first term. That's Hubble-Lemaitre's law. But then there's a second term, which is proportional to z squared. And the second term has a parameter called Q0, and Q0 is related to the second derivative of the scale factor, which means the acceleration. And in the 1970, there was a very influential paper by an astronomer called Alan Sandage. Alan Sandage. Very influential paper published in Physics Today. So how can a paper be influential? Okay, so it's a cosmology, a search for two numbers. So what he says that, okay, all we cosmologists need is to measure two numbers, the rate of expansion and the deceleration parameter. Was the deceleration parameter, right? Everybody believed the universe was decelerating. And this would provide all the information needed for the background universe. So actually something you can do, it's not very difficult, is to plot this exact expression for the luminosity distance for a flat universe for two different values of the omegas. And I did that using Mathematica. So it's not difficult. And here is the, sorry about this, it's not a very good quality plot, but this is the luminosity distance as a function of redshift for two different values of these parameters. And what you can see is that they're very similar to at small redshifts, smaller than 0.1, let's say, but then they start to diverge. And for a given redshift, if you, say, 0.6, you see that if you have a larger distance, it's the universe with a cosmological constant of 0.7. And this is how, actually, more or less, how the accelerating universe was discovered, that the luminosity distance is larger for a universe, for a given redshift. The luminosity distance is larger for a universe with a cosmological constant, which means that objects with the same redshift will look fainter if you have a cosmological constant. And this is how the accelerated expansion of the universe was discovered in 1998 using the standard candles called supernovas. Okay, very simple. So again, apologies for the quality of the plot, but you can do it easily. No? It's just, I can just integrate these things. It was the big surprise in 1998. This was the cover of the Science magazine. The discovery of the accelerating universe was not decelerating, was accelerating. And this is a plot of something related to what I showed, the luminosity distance against redshift. And the data, this is already 2003, again, seems to indicate that this model here on the top, which is a model where you have 25% matter, 75% cosmological constant, was favored against zero cosmological constant. Okay, and that, of course, led to the Nobel Prize, which I already mentioned in the first lecture, to the leaders of two teams. One was the Supernova Cosmology Project, and the other was the High-Z team for the discovery of the accelerating expansion of the universe through observations of distant supernovae. Now I'm going to talk about the other distance, the angular diameter distance, and this has to do with some, if you know some specific size, physical size in the universe. So let's say you have some ruler here which has a size L, and you're observing here. Depending on the curvature of the universe, you can see an angle which is smaller or larger than compared to a flat universe. And so you can define what is called the angular diameter distance through these relations here, and you find that this is also related to the Comoving distance like that. So this is another distance you can measure if you have a standard ruler in the universe, and I talk about the standard ruler a little bit later. So you can imagine, you can ask this question if there's a favored physical scale in the universe, because a standard ruler in the universe would be a scale that's favored. And the answer is yes, there is, and that's called the acoustic horizon scale at decoupling. So I'm going to mention this more a little bit later. And this is the physical scale that sets the angular scale both for the fluctuations in the cosmic microwave background. So there are small fluctuations, and the scale of these fluctuations, the angular scale, is set by the acoustic horizon of decoupling. Also, it's the same scale that is reflected in the distribution of galaxies today. And this is called baryon acoustic oscillations, which I'm going to talk later. Okay, so this is just a result using baryon acoustic oscillations from the dark energy survey compared to what would be a what would be a standard value for this ratio of the angular diameter distance. So this is just to show that the error bars are not small in this case. Okay, so finally, I want to talk about what's called the Hubble Radius or the Hubble horizon. So this is another distance scale that is important in the study of the universe. So we're shifting gears now. We're going back to distances that are important, scales that are important in the universe, and this is going to be important for inflation, for instance. So this is the scale that is given by what light can travel in a Hubble time. So it's naively, that's what it is. So you can really, again, I'm taking the speed of light equals 1. So the characteristic distance that light can travel in a Hubble time is just the inverse of Hubble, of the Hubble parameter. Okay? If you plug in the units with a c, the speed of light here will be correct. And now that's important. So something that's important in the evolution of the universe to describe is what is called the comoving Hubble radius. Remember, I mentioned the difference between physical scales and comoving scales, and that's the scale factor, A. So I have to divide the Hubble scale, which is a physical scale, by the scale factor A to get the comoving Hubble scale. Okay? So remember that age, the Hubble parameter is A dot over A, so the comoving Hubble radius is proportional to 1 over A dot, the derivative of the scale factor. So, but now we know how the scale factor changes with time from the previous lecture. So we can compute what is the behavior of the comoving Hubble radius for different types of domination of the universe. So if the universe is dominated by radiation, you can show from the previous result on that A goes like T to the 2/3, you can show that the comoving Hubble radius grows like A. You can also show that in a matter-dominated universe, the comoving Hubble radius grows like A to the ½ so the square root of A. And you can show that in a lambda, so if the universe is dominated by a cosmological constant, or during inflation, the early period, it's dominated by something that has equation of state -1, and so exponential expansion, so A dot equals A. Basically, you can show that the comoving Hubble radius goes like 1 over A. So that's not difficult to show. So what does that... a nice plot that I think Merdad is going to use, maybe. And this is a plot which is very nice. And this is a plot of the evolution of the comoving Hubble radius as a function of the scale factor. Are you going to use something like this? Sorry? I'm going to use it 100 times. So you're seeing this for the first time, but don't worry if you don't understand, because you see this 99 times. No, or 100. So don't worry. So what is this? So this is the logarithm of a comoving scale. And the comoving scale, guess how a comoving scale changes in the universe? Doesn't change, right? A comoving scale is a constant. So I draw a comoving scale with this black line just to show a given scale. It could be the wavelength of a perturbation. That's something that Merdad is going to use. And then, but what I'm going to plot is this comoving Hubble radius. Remember that if the comoving Hubble radius is in a regime where you're dominated by inflation or something that has equation of state of -1, exponential expansion, it goes like 1 over A. So this is a log plot, so 1 over A is like that. Okay. And then if its radiation is A, grows like A, so inflation has to end at some point. That's the first, one of the last plots of last lecture, that inflation ends, and then the universe is reheated, and then becomes dominated by radiation again. Anyway, so there is a place here where it's called reheating, where inflation ends. So this is a very simplified plot. I'm sure that Merdad is going to do something more sophisticated. But then I put a very sharp transition between an inflationary phase and a radiation phase. And then at some point, you have equilibration between matter and radiation, and the slope changes a little bit from 1 to 1.5. And then you start being dominated by dark energy today, or not today, I think it's 0.5 billion years ago, something like that. And then, or z equals 0.5, sorry. And then the comoving horizon or comoving Hubble scale starts to decrease again, just like that. So what's the important part of this plot is that if you have a physical scale, or comoving scale, a wavelength of a perturbation, it starts maybe outside this Hubble radius, the comoving Hubble radius, and during this period of inflation, it gets, it starts inside. During the period of inflation, it goes outside. Then when the universe becomes radiation dominated again, it goes inside, and then it probably go outside in the future. So that's the meaning of this plot that you're going to see 100 times. What you saw here for the first time. Okay? So, so this is the comoving Hubble horizon plot. Yes. 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 So very good. So let me again let me explain two things here. First, there's a comoving scale, which is, say, the wavelength of a perturbation, and that doesn't change with time because it's comoving. So you're taking out the scale factor. So it doesn't matter what the scale factor is doing. Okay. So now you're asking about this thing here. So why is this going down? So let me go. Thank you for the question. I go down a little bit back here. So again, this is a Hubble, the comoving Hubble scale, comoving. So this is the Hubble scale. To make it comoving, I have to divide by the scale factor. So I'm taking out the expansion. So if I do that, I get 1 over A dot, right? Now, if the universe is expanding exponentially, A is an exponential of time. Guess what A dot is? So if A is exponential with time, A dot is also exponential with time, right? The derivative of exponential is exponential. So it means that A dot equals A, basically. That's what I put it here. So 1 over A dot equals 1 over A, proportional to. And that's why it goes like that. Okay? And you can do the same exercise with the other ones. You get the same, these results. Okay? Nada. Okay, more questions? Okay. So this is the plot that Merdad uses 100 times. And that's, I think that's what I want to say for the first part of the lecture. So how much time do I have? A lot to go now. More questions? No. How many time I have? How much time I have? 15. So I have to go fast. We're shifting gears, and we're going to study now the thermal history of the universe in 15 minutes. So first I will present a brief review of thermodynamics, and then I talk about the effective number of, okay, I don't have to finish this. If I don't finish the relation between the scale factor and temperature, the temperature-time relationship, the origin of the cosmic microwave background, and why we have a standard ruler in the sky. So I start with a review of thermodynamics. That's something that you're familiar with. So if you have gas the number density and the energy density of this dilute, weakly interacting gas with a certain number of internal degrees of freedom, which I call G, is given by these integrals over what's called the phase-space distribution. So f of p is the phase-space distribution, which is controlled basically by the temperature. The integrals that you probably have seen, this is the number density of part of this gas, and this is the energy density. So it all relies on this phase-space distribution, which can be, Fermi-Dirac or Bose-Einstein or Maxwell if you're non-relativistic. So are you more or less familiar with this? Is this okay? All right. So this phase-space distribution for one species that are in kinetic equilibrium is given by this expression. So the interesting thing is that if you back into these integrals, relativistic limit should be much larger than the mass of the particle, and the mass of the particle enters in the relation between the energy and the momentum here. So the integral is in the 3 momentum. So what you get are, you can actually integrate this, you can get exact results for these integrals, and what you get is that the energy is proportional to the temperature to the 4th power. And I'm sure you saw this before. I think it's called Stefan Boltzmann law or something like that. That's the name, right? So that's what you get. There's some factors that you can get from the integrals. And then there's a difference between, if it's plus or minus 1, it's Fermi-Dirac or Bose-Einstein. And it's 1, you multiply by 1 if it's Bose-Einstein, and 7/8. And the number density, the energy density, the number density goes like temperature third power. And again, there's a zeta function, Riemann zeta function here, which is a constant, 1.2. And then is Bose-Einstein, Fermi-Dirac. And with the C, I challenge you, you can compute the number of how many photons of C is in each. This is just this thing here. 3 Kelvin. Right units. Okay? So do this exercise, and you get an interesting number for a conversation in a bar. You can ask your friend, how many photons do you think there is in this glass of whatever beer? That's a good conversation. Okay, so you can do that. You can also do the opposite case where you have a non-relativistic limit, and in this case, the number density decreases, they're in equilibrium, decreases exponentially with the temperature. So this is called exponential Boltzmann suppression. And the energy density, since it's non-relativistic, is just the mass times the energy density. The number density is just this is the energy density. So this is the non-relativistic limit. Of course, you don't need to take all these limits. You can do everything in terms of the integral if you want. But these are very, very important limits to take into account. So for more than one species, the density of relativistic particles in the universe is set by what is called the effective number of relativistic degrees of freedom. So I showed you for relativistic degrees of freedom, the energy density proportion to T to the 4th times the number of degrees of freedom. That's for one species. If you have more than one species, you can generalize this expression with a G star. And the G star is just a sum of bosons and fermions, because you can have both types of relativistic particles. And each type has its own number of degrees of freedom. And here's a very general expression, because I'm allowing different temperatures for each component. So this G star here is a function of time, because as the universe expands and cools, less particles are in thermal equilibrium. They fall out of thermal equilibrium. So this is for relativistic particles that are in thermal equilibrium. So this is a typical value plot of this as a function of the temperature. So as I said, as the temperature drops, so this is 10 to the 5 mega electron volts, million electron volts. and this is 1 million electron volt, and you see that there are these drops in the relativistic degrees of freedom. Now something that's important to define, and I'm sure Julien is going to talk about this. Only a little bit, so I'm going to talk a little bit, and he's going to talk a little bit. And this is what is called the effective number of relativistic degrees of freedom. And this is the relation, so I call this rho r is the relativistic number, the energy density in relativistic degrees of freedom. And that's related to the energy density in photons times this expression here. So there, remember that, look at this expression. There's a 1, and then there's a correction here. So what is this 1? This 1 is just the photons that are around. And what are these corrections? These corrections are for other relativistic particles that are around. Now, what are the relativistic particles that are around? Mostly neutrinos. So we know what an effective is for the standard model. It's from neutrinos, and the value is very close to 3 because there are 3 neutrinos, not exactly 3, because there are some details that I can tell you later. So the effective number of degrees of freedom would be this standard model value plus some other stuff that may or may not be present. This is interesting because this extra component actually parameterizes new relativistic degrees of freedom. And then there's a name, which I'm not sure I like it or not, but people use this name to name this new relativistic degrees of freedom that we don't see. And it's called dark radiation. So just to make more confusing, there's dark matter, dark energy, and now there's dark radiation. Okay? So dark radiation are these hypothetical new degrees of freedom that can change this expression here from the standard model value. Could be an extra neutrino for a heavy neutrino or something like that. Warm, could be warm dark matter, could be something different. And they can be, actually, there were studies of this extra degrees of freedom as possible solutions to the discrepancy of the values of the constant. Now, there is a relation also, yes. Right, it has to be relativistic, relativistic. So dark matter cannot be relativistic because it's called dark matter. So it's something different. Yes. So it doesn't contribute very much to the density of the universe. It's a small contribution. Sorry, say it again. Ah, okay. So they're bounds. I should have put the bounds from CMB. And of course, the bounds are very stringent. So you cannot have. I forgot what the bound is. Maybe delta in F. I don't know, 0.3. So it's 0.3. Thank you, Julien. Yes. Yes, so a coupling constant is the number of degrees of freedom. So that's a good question. And you may be wondering why there's a huge drop here in the effective number of degrees of freedom. This huge drop is because of QCD phase, the QCD confines at this scale. So all these gluons, etc., that were free degrees of freedom, they're not free anymore. So they are condensating to pions, for instance. So that's why you have this huge reduction in degrees of freedom at the QCD phase transition. So thank you. It's not a coupling constant. Thank you. More questions? Okay. So yes, so coming this is very easy. The relation between scale factor and temperature. So naively, I just showed that the relation between the energy density in some relativistic degrees of freedom goes like 2 to the 4th power. That's the Stefan-Boltzmann relation. Now, we also saw that for radiation, the energy density goes like 8 to the minus 4, remember? Instead of 8 to the minus 3, goes to... So you can naively think that the scale factor, comparing these two things, goes like the temperature, the inverse of the temperature. And that's almost true, but there are some factors that you have to take into account because some particles can annihilate into the photon bed. But anyways, this is a good intuition of this process, okay? Temperature, the scale factor goes like the temperature, the inverse of the temperature. And now we can also find, yes. Yes. Yes, I apologize because I'm going too fast on this. But the fact is that what you have, you can show that these degrees of freedom you can have when, for instance, when electron-positron annihilates, they hit a little bit. Are decoupled. So you have to take into account these differences in the number of degrees of freedom. Because when the number of degrees of freedom change, it means that some particles have annihilated, for instance, and they're not present anymore. And this causes an increase in the temperature, a stepwise increase of the temperature, actually. So that's why it's not exactly T to the minus 1, A to the minus 1, but you have to take into account this little bit hits that occur when particles. Right. Thank you. Yes. Sorry, this was not very precise because I didn't have the time to go into this. But, yeah. More questions? So here's something very useful if you want to have an idea of relation between temperature and time in the universe. So some people say, okay, when the universe was at very high temperatures. By the way, how do we measure temperatures in the universe? It's not Kelvin anymore. In the early universe, we use GeV or MeV to measure the temperature. This is just for you to remember. So the first equation, there's a relation between, again, the Hubble parameter and the energy density. But remember, the energy density for relativistic particles, radiation, is T to the 4. So the square root of T to the 4 is T squared. So there's a relation between Hubble and the temperature of the universe. But again, Hubble is like a T to the minus. And then comparing these things, you find that the temperature goes like the time to the power minus 1/2. You just have to compare these things here, right? Hubble goes like T to the minus 1, and goes like temperature squared, T to the minus 1/2. And actually, you can plug in numbers, and that's a very good number to have in your head, is that the temperature in mega electron volts, in million electron volts, is like a 1 second, more or less 1 second. So when the universe had a temperature of 1 million electron volts, this happened when the universe was about 1 second years, 1 second of age. 0 age? 0 seconds. Okay, so I will stop here. This is a lot of that I took from my favorite book in cosmology still is Cobb-Turner. That shows how old I am. I still like Cobb-Turner. And this is art, this is art. Because I have to tell you, there was a person at Fermilab who was in charge, an artist, was in charge of making all the plots and all the posters. I forgot her name, but she's amazing. There's an exhibit of her art. And this is art. So this is her art. And this you can see the evolution of the universe in different parameters. This is temperature. So this is 1 Kelvin. This is measured. This is energy. So 1 millielectron volt, 10 to the 6 gigaelectron volts. This is density of the universe. So this is 10 to the minus 30 grams per cubic centimeter around the today, which is the critical density. How it grows. And this is time. So this is, for me, this is a beautiful plot. And there are different places here where you can see the quark-hadron transition, Big Bang nucleosynthesis, matter domination, etc. So all of this you can get now. With all the information I gave you, you can do this plot. Believe it or not. Not as beautiful as this, but you can actually estimate, if I give you, okay, what is the energy density of the universe when the universe was 1 second? You can do it. You can do it now, hopefully, okay? If you get all these lectures, you can do it. Okay, so I stop here, and then I think I still have some things to go, but I'll do it next time. Thank you. Or the age of the universe. You have to assume that there was a t equals 0, yes. There's a t equals 0. It's here. I mean, it doesn't matter really, because if you know the integral from t equals 0 to t to the minus 42 seconds is irrelevant. It doesn't change anything. Infinite. Yeah, density is infinite. So it's a singularity. So yeah, that's a good question. We don't understand. I'm not pretending that I understand. So if we understand what is the beginning of the universe, the very, very beginning, I have to say we do not understand. Why we do not understand? Because our physical laws are not tested. We don't have a physical law or a physical theory that goes all the way to the singularity. We just don't. So let me say it now, because I think this is important. The laws that we know were tested in the universe until the first few minutes. So that's Big Bang nucleosynthesis. Before that, we don't have any probe of the universe that we can test our laws at this moment. So all I can say is that from 3 minutes to 13.7 billion years, we have a theory that agrees with the observations that we have so far. Before 3 minutes, we don't have any probes that actually proves or disproves the theory. This can change, hopefully with inflation, if we have signals from gravitational waves, further gravitational waves, then we can probe further. But we can never probe t equals 0. Right, so this is extrapolation, the radiation-dominated behavior. Have the parameters today, more or less, you can compute everything here. So that's what I told you. If you have omega matter today, omega lambda today, omega radiation today, you can compute this. And you can do it with the tools I gave you in these lectures. Okay? So why do they go back in time? It's because inflation. That's the only reason, because we don't have any probes on this. We don't have probes up to a few minutes here. Yes? How? So in the current situation that we have now, it's the cosmological constant that is driving this inflation. So what is this cosmological constant? We don't understand what is the cosmological constant. But the basic idea is that it's energy of the vacuum. So it's a constant energy of the vacuum. And this is what is driving the universe, the inflation, because you get more space, you get more energy because of this cosmological constant. So I'm not sure if this answers your question, but again, what is driving the accelerated expansion today, as far as we know, and we have tested, is a cosmological constant. It can be something different, but the model of a cosmological constant explains what we observe today. No, no, it's just accelerating. There's no reheating in this inflation now. As far as we know, there's no reheating, so we're just inflating away. So it's very different from the inflation that Merdad is going to talk about, the beginning of the universe, where you have reheating and it's not a cosmological constant, it's a scalar. Well, we don't know what it is, but the simplest model is one scalar field. There can be much more sophisticated models, but one scalar field, and then the energy density is concentrated in the potential of the scalar field, and that the scalar field has to be coupled to the fields that we know about, so that they can transfer energy to the fields we know about. So we don't know if we have the same thing happening today in this inflationary phase today, but we can test. And the test we have so far says that cosmological constant is sufficient. It may change, okay, as we increase our precisions, etc. There's already some tension in the Hubble measurements of the Hubble constant. But as far as we know at this point, if you're talking about lambda CDM, the standard cosmological model, there's no reheating. So this inflationary phase will last forever, if there's no other minima. So we can discuss this later. It's very interesting to discuss these things. Anyways, I'm giving the party line, right? The most conservative thing that you can imagine, that if it's lambda CDM, it's just a cosmological constant, pure cosmological constant, it will continue forever. So we enter inflationary phase and will continue forever, which means that our horizon is going like this, right? The Comoving Hubble horizon is going like that, and we are going like this. So we are going to cross the horizon. We are going to cross the horizon at some point, the Hubble horizon, right? Yeah. Sorry about that, but that's the truth. For others too, please.
So now we can take the, you know, I have two.